Hi everyone, we're moving into chapter 13 here in Calc 3. Chapter 13 is on vector valued functions and motions in space. And in section 13.1 we basically want to talk about curves in space and tangents to these curves. So there's technically only one example in this section, by the way, even though there's 5 pages of notes, because I'm spending a lot of time just explaining how everything works to you. So I will label these videos as the example in this section is example 26. I will label these videos as example 26A, 26B, etc. But not all of them will have that example, correct? I just want to keep the videos not too long as we go through probably page by page. Okay, so when a particle moves through space during a time interval I, we think of the particle's coordinates as functions defined on that time interval. So x will be a function of time, y will be a function of time, z will be a function of time. This author calls them f of t, g of t, and h of t. They represent the x, y, and z coordinate at that specific time t. Some authors will write it x of t, y of t, and z of t. This author writes it as f of t, g of t, and h of t. So the points x, y, z, which are f of t, g of t, h of t, where t is in that time interval that we're interested in, make up the entire curve. And we call this curve the particle's path. So you can imagine there's the particle at time t, which has the coordinates x of t, y of t, and z of t. And then this is kind of the overall curve that this particle is traveling. And I drew this because I'm just trying to show that this part goes behind that one in front of us. Remember, we're trying to draw in 2 dimensions what a 3-dimensional path would look like. But the vector r of t, which, remember, if I'm drawing a vector from the origin to a point, then the components of that vector are the coordinates of its terminal point. So the vector r of t would be f of t, which is, okay, I wrote it as x of t here because that's more comfortable to me, but this is x of t and f of t are the same thing. G of t, y of t are the same thing. H of t, z of t are the same thing. I got carried away because I'm used to writing it like that, even though the author writes it as f of t, g of t, h of t. So that's the vector r of t, which represents the terminal point of that vector represents any point on the particle's path. The following are some interesting vector valued functions that we can visualize through good graphing software, and we typically, when we're learning calculus, we look at these types of functions. The first of these are called helices. A singular graph or singular path is called a helix. By the way, these first 2 pictures are the same thing. I just want to show you how the helix works. It basically travels on a path on the outside of a right circular cylinder like this. Okay, so its vector valued function that describes that particle's motion is r of t, which is cosine of t in the I direction plus sine of t in the j direction plus tk. So the cosine t, sine t for the x and y components make it travel around on a unit circle. So this circle is x squared plus y squared equals 1. But with the t in the k direction, it essentially travels around with the radius of the unit circle, but it starts to rise up. Okay, so you can kind of visualize that right here. And this is the visualization with the cylinder drawn in, just to kind of show you how it's working. Now, of course, so if I keep the x component and the y component the same, like in this example, you can see that, okay, it still travels around the unit circle. And instead of having t in the k direction, it's 0.3 t in the k direction. It means it doesn't rise as fast. Or if I make the argument of the cosine and the sine different values, like 5t in this example, what that does is it makes it travel around that unit circle faster. So even though it's rising with the original example of t in the k direction, this travels around the unit circle much faster, so it also compresses it like that. These are kind of looking like slinkies. I don't know if you've ever seen a slinky. When I was a kid, there was a toy called a slinky. You could walk it down the stairs. It was pretty cool, but they were essentially helices.